All right, thanks for your introduction. Good afternoon, everyone. My name is Houxiang from UIUC. Today, I'm very delighted to present our paper titled STYX, Exploiting SmartNIC Capability to Reduce Data Center Memory Tax. So here is the outline for my today's talk. First, I will talk about the data center memory tax, and then I will talk about memory optimization kernel features and about their goals, operations, and their side effects. Then I will present our work, STYX, and I will tell you how it works and several feature-specific optimizations we have for it. Finally, evaluation and conclusion are provided. OK, let's get started. Nowadays, there are two notable trends in data center memory. The first one is the stagnant DRAM technology scaling leads to a stop in the price reduction in DRAM. Here is the plot. On the y-axis is maybe the leader is too small. So the y-axis is the price per gigabytes for DRAM and on the log scale, and the x-axis is the time. As you can see here, around 2010, the prices remains very stable, relatively stable compared with the over past 50 years. It's not good news for the DRAM consumer, actually. And another trend is that there is an increase in memory demand in data center. Here I give you a plot which tells you about the capital cost and power cost of memory as a percentage of the rank TCO and power across several generations in the meta data center. As you can see, in the latest one, there's about 1/3 cost for the power and the capital is divided into the memory part, which makes the memory becomes a very dominant part in data center cost. With these two challenges, it's very urgent for us to find some solutions to elevate this burden of memory resources in data center here. So people find some ways, especially from the OS community. People propose several memory optimization kernel features. And here I will highlight two of them. The first one is kernel same page merging, also called KSM. KSM aims to merge pages with the same content, and then you eliminate the redundant page. You can save the host memory, and for your system, you don't need to buy more memory, but now you can still hold more virtual machines. The second one is compressed cache for swap pages, also called zswap. zswap compresses and stores the swap out pages into a RAM cache instead of our common backup storage like disks. With zswap, the system can serve the page fault more quickly if you have a hit on this RAM cache. And also you have less disk I/O traffic with zswap. And there are many more other kernel features, and these features are proven to be very efficient, and they can improve the efficiency of the whole system very effectively in the system in the data center. They have some real world profiling paper. You may find it later in our paper. So here I will give you more details about zswap, and I also use zswap for following impact analysis here. So let's see, what's the difference between swap and zswap? So let's see, as I mentioned, zswap will compress the swap out pages and store it in a RAM cache instead of disks. And here is a plot for the common swap out and swap in process. If you have a swap out pages, you will write it to disk directly, and if you want to swap in, read it from disks. Differently, zswap will preserve a cache in a memory called zpool here, and when you have a swap out page first, zswap will do a compress on this page, and then it stores the compressed page into this zpool. Similarly, if you have a swap in, the decompressed page will get decompressed first, and then you write the full page right back into the memory. And here we can see the major two operations involved in zswap is page compression and page decompression. And if you compare the two plots on the left and on the right, you can see that there's no disk I/O involved anymore in zswap. However, the memory kernel features, the memory optimization kernel features like zswap, they are not free. We identify two major sources of their overhead. The first one is CPU cycle consumption by this kernel feature, and also the cache pollution brought by these kernel features. These features can significantly interfere with the co-running memory-intensive or latency-sensitive applications at server CPUs and server caches. And here, let me give you a direct view of this impact. Here, I take zswap as an example. And on this plot, the y-axis is the CPU cycle consumption by different processes. And the x-axis time is a time. We take a snapshot of the system status here. So you can see the blue area is for Redis, orange area is for zswap. When zswap starts at around 71 seconds here, the CPU cycle consumption increases a lot, more specifically by 26%. We also measure the last level cache miss ratio. And similarly, when the zswap starts here, you can see a huge jump in the last level cache increase. And we do some average calculation during this zswap time period, and it's about 49% compared with 4% when there's no zswap running. And finally, let's have a look at the impact on the response latency of Redis. So Redis is our target application here, and we box the y-axis is the latency for each Redis request, and each box has about 1,000 requests. So the box shows the first and third quartile range of the latency request latency values, and the triangle one and the horizontal line means the median and mean values of this request latency. And during the zswap runs, we can see that the 99% latency can increase by 2.1 times, while the mean latency can increase by 1.5 times. It's quite significant degradation with the performance for these applications which are very time sensitive. So now the question is, how can we elevate these negative impacts, but still enjoy the benefits of them? And here's our approach to explore the SmartNIC capabilities. Let me give you some background about SmartNIC quickly. SmartNIC are network interface controllers with a CPU, ASIC-based or IPZ-based accelerators, memory, and I/O subsystems. So here, I would like to highlight two capabilities. The first one is compute capability. So as you can see, the CPU cores, ASIC-based accelerator, or IPZ-based accelerator, and there are many other variants of SmartNIC nowadays. These components can provide enough or sufficient computing resources. And the second capability is RDMA capability. RDMA is short for remote direct memory access. With RDMA, the data transfer between two machines do not need to involve their CPU anymore. And another good news is that SmartNIC is already deployed by hyperscalers. So it's very possible for us to use our mechanism in a data center. So now I will give you more details about our design STYX, and I will let you know how STYX leverage the SmartNIC. So STYX framework is built based on the key observation, which is memory optimizing kernel features can be decomposed into control plane and data plane. Here I will show you a conventional workflow of one operation called page comparison from KSM. So KSM will compare two pages to see whether they are sharing the same content, and then it will decide whether to merge them or not. So let's see. For the first step, KSM will tell CPUs which two pages it wants to compare. Then you read the two pages from host memory. But pay attention here. For the last level cache, it gets polluted by these two pages. And then the page comparison will take CPU cycles to do this. We'll take the CPU cycles to do this byte-by-byte comparison, and then comparison result comes back to KSM process. So we classify the first and the last step as control plane, while the second and the third step as data plane. So in STYX, we propose to offload only the data plane operations to the SmartNIC. And here, let's see how STYX works step by step. The first phase is setup. During setup, user can determine which functions you want to offload from these kernel features. And for zswap, here we select compression and decompression. For KSM, we select checksum calculation and page comparison. Server CPU will establish the RDMA connections for each function. And then both server CPU and the SmartNIC CPU, they will create STYX descriptor, which consists of pointers to starting address and lances of memory regions where the function will operate on, and also pointers to the RDMA connection resources. You can find more details about this descriptor in our paper. We only need to go through this setup phase for one time when the system starts up. So the overhead of the setup is amortized. Okay, so the second step is called submission. So when server CPU updates, when the KSM runs on the server CPU, and it encounters the function you want to offload, first, the server CPU will update the descriptor. For example, it will tell the descriptor which memory area I want to work on, and then issues the RDMA requests and suspends the kernel features. The third stage is remote execution. SmartNIC will do RDMA copies these memory regions from host memory to SmartNIC memory without involving any CPU cycles on host side. SmartNIC CPU will execute the corresponding functions on these RDMA copied memory regions. And then you can see with this blue arrow, we will write this result back to some specific location in the SmartNIC area. And then SmartNIC will read from that location, read that results, and send it back to host CPU, and also place it in the host memory. Then server CPU will get notified that the result is back, you can continue. So server CPU will resume the execution of kernel features based on this return result. For example, for KSM here, you can decide whether you want to merge the pages or not. So we demonstrated the effectiveness of STYX after re-implementing these two kernel features in Linux kernel 5.4. The changes in kernel are very minor. For example, in this pseudocode snippet, for zswap, we just replace the functions. The original is page compression, page decompression. We just replace two functions. And for KSM, we just need to locate the page comparison and checksum calculation function person, and then replace them with our version. The STYX version of this page comparison, page decompression function, they share the same interface with the original functions in kernel, which can help to minimize the modification or influence in kernels. In summary, STYX can be easily integrated with any Linux memory or computer-intensive kernel features as a general framework, and it's not limited to the examples I'm showing here. Okay, and now we come to the evaluation part. So we target at the latency sensitive workloads here. We run YCSP workload with Redis, and on the right, the table shows our system setup. We use Intel Xeon CPU with NVIDIA BlueField 2 SmartNIC. And I want to highlight that this BlueField 2 SmartNIC has 8 ARM cores, and both of them are run with Linux kernel 5.4. Okay, here are some results. First, I saw the 99% latency of Redis requests. In this plot, the y-axis represents the latency normalized to the baseline, where there is no kernel feature running, and also the lighter column is corresponding to the cases when the KSM or zswap runs, and the column with darker colors is when STYX is involved. So we can see that STYX can successfully reduce the 99% latency increase. For KSM, it reduced the overhead from 6.24 times to 1.11 times, and for zswap, it can reduce overhead from 8.70 times to 3.05 times. And let's see why we have this significant reduction in latency. Here, we still attribute this success to our reduction in last level cache misresolve reduction and CPU cycle reduction. So let's see the LLC administrator first. So on average, STYX can reduce the LLC administrator from 58% to 30% for KSM. I mean, on average across all 4 workloads here. And for zswap, it reduces from 35% to 26%. We also measure the CPU cycles consumed by these 2 features. And the y-axis is the percentage of the CPU cycles consumed by the kernel features in the total CPU cycles consumed by both applications and these kernel features. And again, in average, we can reduce, STYX can reduce the CPU cycle consumption from 26% to 7% for KSM, and for zswap, it can halve the CPU cycle consumption from 20% to 10%. We also analyze several other metrics, like so for example, the offloading path latency analysis. We measure the latency for each step and see which is our new bottleneck now. So currently, we find that the third phase, remote execution, takes more than 75%. We may do further optimization here. And also, we measure the impact of STYX on the effectiveness of these kernel features. And fortunately, we only see negligible performance degradation brought by STYX. You can find more details and numbers in our paper also. And in Datacenter, there could also be some applications running on the SmartNIC. So we also see the STYX impact on this co-running application on SmartNIC. And as we can see here, STYX only utilizes about 30% of a single core, while this Bluefield 2 have 8 cores. So the computing resources is not very fully utilized there. And for this application, we only increase the 99% of latency by less than 2%. So here is the conclusion. So first, memory optimization kernel features are very useful, but it can interfere with some co-running user space applications and significantly increase their 99% of latency. And for our work, STYX framework, it leverages the compute and RDMA capability of SmartNIC to reduce this interference by offloading some memory or CPU-intensive operations to SmartNIC. STYX can not only preserve the benefits of these kernel features, but also reduce the 99% of latency of these co-running applications by more than 50% here. All right, thanks for your attention, and I'm happy to take any questions.